calculating the definite integral here, I have to take a look at this function and I need to make sure that I can actually integrate this. Now, since it's a monomial denominator, this makes it a little bit easier because if I can just isolate the powers on the x's in the numerator, I can then just simplify that. So that's what I'm thinking I'm going to try doing here. So I'm going to expand this in. So this becomes x to the power, and it's going to be 1/3 plus 2. So that's going to be 7/3. So 2 is 6/3 plus 1/3 is 7/3. Plus, this is going to be x to the power 1/3, and that's going to be all divided by x to the power 1/2. And that's times dx. Well, if this is the case, all I have to do is subtract these powers. And when I do that, I isolate each power term. So 7/3, get a common denominator, becomes 14/6 minus 3/6. So 14/6 minus 3/6 is going to be 11/6 is my power, plus 1/3 power minus 1/2. Okay, so that's going to be 2/6 minus 3/6, which is -1/6. So now I've now expressed this all just as a power. Well, I can just use power rule now. So when I integrate this, I'm going to increase the power by 1. So this becomes x to the power 17/6, and then divide by 17/6, I get that expression. I'm going to increase the power by 1, so this becomes x to the power positive 5/6, and then I'm going to divide by 5/6, which gives me 6/5. Now I could just I can just put this into my calculator and I can calculate this integral. Okay, so I'm just going to plug in my bounds. This works out to be, plugging in the bounds here, I'm going to write this in, so 6/17, 3 to the power 17/6, plus 6/5, 3 to the power 5/6. That's going to be the first part of that, minus, this is going to be, plugging in x equals 1, I get 6/17 plus 6/5. Okay, so this, really we should do this with the calculator. 6 divided by 17 times 3 to the power 17/6 plus 6 divided by 5 times 3 to the power 5 divided by 6. Okay, and I'm going to then subtract 6 divided by 17 plus 6 divided by 5. And I end up with the definite integral value works out to be 9.379. So I'm going to round that to 9.38. Okay, so that would be the area under that curve. Here I have sine of ln x over x. I've actually drawn this graph here, and we want to find this area from 1 to, the area under this curve from 1 to 10. So this is this area in here. So 1 is at intercept all the way up to 10. So this is what this is going to look like. Maybe I can kind of estimate there if I want to count the grid here. To do this, this is not a standard integral, so I need to look for a substitution. I try my embedded function first of log, and if the derivative of this accounts for the remaining term, oh, yep, I've got x and dx here, that my du can be replacing that part there. Now, with definite integrals, when we switch variables, we do have to make sure that we are stating that the x here, the bounds are in terms of x and not in terms of u. So I need to do that. This becomes sine of u, and then I can replace the dx over x with a du. This can be easily integrated, so again, I'm going to keep my bounds. So this becomes negative cosine of u, and my bounds are x equals 1 to x equals 10. I'm going to replace my u with my original log x. So I'm going to put that back in there, log x. And now I can put my bounds back in terms of x, so I don't need to put those x equals 1 and x equals 10 in here. So just plugging this in now, this becomes negative cosine of log 10 minus negative, so plus cosine of log 1. Okay, log